Now, the determination of the magnitude of the electron charge, that is due to R.A. Millikan in a famous experiment carried out in 1909. And this one is really clever in terms of getting around things that you don't quite know through a very clever analysis. So here, I'll show you how this experiment is done. So you begin with a fine mist of oil droplets. So you can use one of these misters. It's basically like it's got a container with some oil in it, right? It's got like a little spritzer bulb on the back end that you can squeeze, and a little metal nozzle, and when you squeeze this, what you get is, they used to call this like an atomizer. It doesn't atomize things, but it gives you an extremely fine mist of oil that is then spread into the air. Now, the other fascinating thing about this is that there's an interaction between the metal nozzle and these oil drops, so that once again we are able to coax these negative charges out of these metal atoms, and you end up then with these charges in differing amounts on your various oil drops. And the whole premise of the experiment then is to measure exactly how much charge there is. And the way the measurement is done is that once again we use a parallel plate capacitor, and we apply a known voltage to it, which will then create, this will be the positive end and the negative end, a downward electric field. And the strength of that electric field is easily determined, right? It's always the applied voltage divided by the separation D between the plates. Now, the way this experiment is done, because these are super tiny oil drops, you shine light in so that you can see them, and then you observe where you see them with some kind of a microscope. And then the idea is basically we're going to turn this voltage knob to try to balance then the gravitational force against the electric force, and use that to gain information about the charges on these particles. Now, a few key observations come out of this experiment, a few things that we really need to know about this. So the first thing to know is that these are extremely small droplets, so that even when you look at them in the microscope, you can't see how big they are. All you see basically are these little shimmering dots in the air. So the drops are too small to actually see or measure the radius of the drops. Now the next thing that we observe is that we can balance the gravity and the electric force. The electric force, of course, is Q times E, and we can actually get these guys here to hover. And that gives us, of course, then some very key information. If we can get them to hover, we can then begin to figure out how much charge actually it is that they are carrying. Now, let's see what happens when we begin to try out an analysis. Now, leave a little bit of space here in your notes because I'm going to make a few other observations as we go along, but I'd like to begin to jump in on the analysis. So if we begin to look at the analysis here for this experiment, of course, we want to think about each drop. So if we make a nice proper free body diagram for one of our drops, we need, when he's hovering, so this is the case when we're in a hovering situation. And when it's hovering, it's pretty simple, right? The forces must add up to 0. So we are directly balancing then the downward gravitational force mg against actually the electric force, which is in the upward direction, because we've already determined that these are negative charges. Actually, I should say the fact here that we can get them to hover when we have a downward electric field tells us that these must be negative charges for that electric force to actually be upward, because negative charges like to climb upwards on electric field lines. So from this, that we conclude that we can get them to hover, and we can conclude that the charge is less than 0. These are indeed these negative charges that we are looking for. Now, as we analyze one of our hovering situations, the upward force in magnitude, I'm just writing the signs here. We've already figured out the various directions of things. In terms of magnitude, that's the charge on each drop times the magnitude of the electric field. So then, because this is hovering, we have a charge balance. So then Q times E is going to be balanced directly against the mass of each charge times gravity, g. And that, of course, is going to make it very easy for us at the end of the day to actually solve for each individual charge. It'll just be the mass of each drop times g divided by the electric field. Now, here is where we face a problem. One of the key problems that we are facing here, actually, is the fact that we don't know how big the droplets are. So we don't know their masses. So we're going to have to be very clever about the value of how we determine that. Now, one of the ways to do that is to actually simply turn off the voltage, and then you can take one of your hovering drops and watch it fall. And these drops, because they're so tiny, the viscous force turns out to be very important, so that they very quickly, as they begin to fall, reach a terminal velocity. And you can measure that velocity, because even though you can't see how big they are, you can see where they are, and therefore how quickly they are falling. Now, just before we turn off the voltage, though, there's a third interesting observation. This third observation is the fact that while you have someone hovering, the hovering drops sometimes, and very key here is they sometimes suddenly start moving. The reason they suddenly start moving is that they are beginning to pick up little bits of static electricity from the air. They're either giving off or picking up charges. But they don't, when you're watching it hover, it doesn't suddenly start drifting up or start drifting down, as though this charge is being transferred continuously. It's always suddenly it starts dropping, or suddenly it starts climbing. That tells us, therefore, that we are dealing with various discrete charges. So we have very clear evidence that the charge is coming on and off in these some kind of discrete units, a particle-like type of behavior. Now, the final observation I just want to make here is that when we turn off the voltage, you can actually measure, because you can see where the drops are, you can measure the terminal velocity, which we will call V. So this then gives us the key piece of information we need, because the terminal velocity is going to end up depending upon the size of the droplets, so that then we can determine their mass and ultimately their charges. So let's continue our analysis. So the second piece of analysis is now we need another free body diagram. This is when we are in a terminal velocity type situation. And in this situation, the forces that we are balancing are, once again, of course, we have gravity downwards. There is now no electric force involved, but there is a drag force. And that drag force comes from the viscosity of the air. But at this point in history, we knew quite a lot about fluid mechanics, and that viscosity is very simple. It's related to 6 pi times a parameter known as the viscosity of air, which was easy enough to measure. So this is the viscosity of air, times then r, so it does depend upon the size of the drop. And finally, it's your standard drag force that is simply linearly proportional to the velocity. So when we're in a terminal velocity situation, once again, we're not accelerating, so our forces are in balance. And so this mg that we need in order to determine the charge on the electron, right, also must balance by looking at this second situation against the terminal velocity which we observe. So it's going to be this 6 pi eta RV. Now, just to make the algebra a little easier, since this is here just a constant, let me call this combination of parameters alpha. So mg then will just be some known constant characterizing the air times the unknown radius of the droplet times the observed velocity, the observed terminal velocity. So this gives us one equation to try to determine the mass of the particle, but unfortunately we've just introduced a second unknown, the radius of the particle. So to close the loop, we need one more equation so we can solve for our two unknowns. We need another equation relating radius and mass, and that's simple enough because we also know the density of oil. So the mass of the droplet actually is going to be its volume, 4 pi on 3 times r cubed, right? So I can relate it to my one unknown of the radius, and that then multiplies the density of the droplet rho. And this term also, of course, includes the gravity g. So that's mg in terms of radius, and that equals alpha rv. So now we have a single equation that we can solve for radius, and it's actually not too hard to solve. We can pretty much do it in our head. If we move the radius to this side of the equation, we will have r squared. That means when we finally solve for the radius, r will be the square root of something. And that something will be when I get all of the known values on the left side of the equation over to the right side of the equation, and that's going to make a fraction for me. On the top of the fraction, I will have the alpha v that began on the right-hand side of the equation. I will also have, when I divide through by the factors on this side, because 3 is on the bottom over here, it's going to show up on top over here. So that will be 3 alpha v on top. And then on the bottom, I have the rest of my factors, 4 pi times rho g. Perfect. So now I know the radius. And once I know the radius, all I need to do to determine what I need, my mg, is to substitute this radius in here, and then I will have everything in terms of known quantities. So when I make this substitution, I want you to notice I have a square root alpha v in the numerator and a second factor of alpha v here. So at the end of the day, I'm going to have alpha v to the 3/2 power. And then the remaining factors here, because I already took care of this alpha and v, are the non-alpha v parameters inside my radius, which will be this square root. So it's going to be square root of, there's just a 3 left on top, and I still have my 4 pi rho g on the bottom. That then is the value of mg, and to get q, I just divide this by the electric field. So the final expression is then q equals this quantity here, square root 3 over 4 pi rho g times alpha v to the 3/2. Well, this is the only place where alpha appears, so I might as well put in its official values. Alpha is 6 pi times the viscosity. That then is multiplying a factor of v. That appears to the 3/2. And finally, all of this is divided by the electric field. So beautiful, right? I've got the charge on each drop in terms of everything I know. There's numerical constants, density of oil I know, gravity I know, viscosity of air I know or can be measured, electric field we can determine from our voltage, and the velocity that we see the thing falling with. Perfect. So that gives me my determination of the charge. So now let's take a look at our results. So what we can do is for each drop that we are able to make hover, we can then make a determination of its charge. So the way you would plot the data is you would plot charge here on this axis, and on this axis I'm going to plot the drop number. But I'm going to play a trick. I'm going to number my drops in the order of the amount of charge I see. So the least charged drop I'll call number 1, the next one I'll call number 2, and so forth and so on. So this is going to be the drop number, but it's sorted drop number in this direction. And here's what we're going to see. So we will never see anybody with 0 charge because those wouldn't hover for us. We will see, we may or may not see some with just 1 electron on them. So we don't know where we will begin, but we'll begin with some value. And then there are certainly other drops that had similar numbers of electrons, but just because of experimental uncertainties, I might see a different velocity for those. So there's a little randomness that I see. So, and because I'm sorting these in increasing order, I'll have basically a constant plateau, but that is just sloping upwards slightly. The real kicker, though, is at a certain point, I get to the last drop with that number of electrons, and there's a sudden jump, and I now have the next drop with some other number of electrons, and he has his own plateau, and it continues this way, so forth and so on. Now, We can't guarantee that the least charged drops had just one electron on them, but we can see these very clear discrete steps. So this change in charge between the steps, and you can basically take the average step size that you see. This corresponds to the charge of a single electron. So we can now officially call that amount of charge E, the electron charge. And the value for E, the official value, Millikan had something fairly close, but the official value for the charge on the electron is 1.602 times 10 to the minus 19th coulombs. Now the second really cool thing about this is we've got an absolute charge for the electron, right? But we already had all the way up here, right, from Thomson, we already had the charge to mass ratio of the electron determined. So if I take charge and divide by charge to mass ratio, I actually can figure out then the mass of the electron. And I'll write that down for you in just a moment. But then also notice that also gives us the mass of the proton because we knew its ratio. It's 1,800 times larger than the mass of the electron. So all kinds of great information now is coming out of this analysis. So the mass of the electron, when you do that division that I was just talking about, will come out to an official value of 9.11 times 10 to the minus 31st kilograms. When I multiply that by that 1800 ratio, I'm now also getting the mass of the proton, which turns out to be about 1.66 times 10 to the minus 27 kilograms. So now I know the mass of one of the atoms, and we already knew the mass ratios of the atoms. So now we've weighed, in fact, all of the different atoms. And another key way to express that concept is now we know how many atoms are in a mole, right? Remember Avogadro's number, script n sub naught, and the number of atoms in a mole is equal to the number of hydrogen atoms in 1 gram. So here's 1 gram mass, and I divide it by the mass of each individual proton, which is 1.66 times 10 to the minus 27 kilograms. And when you do this division, you can see I'm basically getting 1 over what looks like the decimal expansion for 1/6. So I actually get a numerical value that's like 6, but it's 6.022. And if you track all of your factors of 10 very carefully, it's times 10 to the 23rd, and we get the Avogadro's number out of this. So we don't get just one important fundamental constant. We get 1, 2, 3, 4 fundamental constants out of this. And this is one of the reasons why this beautiful experiment, when you think about the trick of using the viscosity to track the falling particles, this is one of the reasons why this was a big component of Millikan winning the Nobel Prize. And he was the first American, actually, to win such a prize.